Now, identifying those isn't necessarily something that is common practice. A lot of times computer software can work on this, but understanding what's going on, being able to see, hey, this part of the rock had a different strain path than that part of the rock, can help you picture what something used to look like. So, practical concepts. What can we do with this? Can we quantify it? Can we actually calculate anything other than just drawing these weird circles and ellipses with lines in them? Well, there are 3 measures of strain for quantified values. There's longitudinal strain, volumetric strain, and angular strain. So let's look at the longitudinal. This is a pretty simple one. This is something that we actually have seen in life before. Think of a rubber band or an elastic in your waistband of your pants or something like that. When it gets stretched, it changes length. Same with a spring. When it gets stretched or compressed, it changes length. We have special terms and equations for this. E is the elongation value, and it can be positive or negative. If it's positive, the thing got longer. If it's negative, the thing got shorter. And what we do to calculate E is we take the length after the fact, what it is now, post distortion or length final, and we subtract the length initial. Then whatever value we get, we divide by the length initial. So E is length final minus length initial divided by length initial. Sometimes E is converted into a percentage instead of being a decimal, and so then you just take that raw E and you multiply by 100%. So if you get 0.6, it's the same thing as 60%. Volumetric strain is called delta. Now this can get a little confusing because this is the same symbol that we use for saying like delta V for difference in volume. But in this case there's no letter after it, it's just the symbol, just delta. So delta is volumetric strain, which is different than if we said delta V for the difference in volume. Because if you look here, we have volume, what it is now, minus volume initial, which would be delta V. That's the change in volume. So this isn't the same thing. Delta is calculated just like the E was calculated for elongation. Volumetric strain delta is volume final minus volume initial divided by volume initial. If it's positive, it means that it got bigger. This happens like, for example, if you have a balloon and it gets warm, it expands. There's volumetric strain. Delta is positive. A negative result is volume loss. This is much more common in the ground because there's a lot of pressure. You add pressure, the volume decreases, and you get a negative delta. Angular strain has to do with shearing because the angles are changing. Pretty straightforward. The change in angle between two lines that were initially perpendicular. So these initial strain axes, if there's shear, if there's general shear, they change angle, and we can figure out the angular strain. Now, tau is angular shear. It's the little thing, sort of looks like a letter Y with a line extending up higher. Some people think it looks like a martial arts weapon called a sai. And wow, okay, because it is psi, tau is a different letter. I'm sorry. This is the Greek letter psi because it looks like the martial arts weapon called a sai. And it is angular shear. Now, to get this, we use... Okay, let me start over. I'll go back and edit this afterwards. Anyways, let me start this slide over here. Angular strain. The change in angle between two lines that were initially perpendicular, such as the strain axes. They were initially perpendicular. If there's general shear, they change angle. They're no longer perpendicular. That angle is called angular shear, or that change in angle is called angular shear, and is given the Greek symbol psi. It looks kind of like a capital Y where the line extends up higher through the center, or the easier way to remember it is that it looks like a martial arts weapon, little sword called a psi. So that change in angle is called psi, and then we can calculate shear strain by taking the tangent of psi. So gamma, angular strain, or a shear strain, is the tangent of psi, where psi is the angular shear. So how do we use this? Still, all I've done is throw symbols and diagrams and terms at you. What is it good for? That's what we care about, right? Why would anybody do this if it wasn't useful? Well, one of the things we can do is use it to reconstruct the original tilt of beds based on ellipses that used to be circles. How do we know they used to be circles? Well, there are certain concretions and certain fossils, for example, that always form in circular or spherical shapes. I say spherical because then when you cut through it, of course you're seeing a circle. So if above the tilted beds there are things that should have been circular, but they're elliptical, we know there was compression. Because they're in the bed above the tilted beds, we know that they're newer than the tilted beds. And since they're deformed, the deformation is newer than the tilted beds. The whole, superposition thing. So that tells us, hey, you know what? There were angle changes because of this compression. These beds used to be at a different angle. What was that angle before the compression? That's taking it back one step in the strain path. The tilting, of course, was a whole different strain step. Also, it can be used to reconstruct the original shape of a fossil. If you've got a concretion next to a fossil, the concretion is something that always forms a sphere. It's now an ellipse. The fossil is something you don't know what it used to look like because maybe it's new. It's a new discovery, or you hope it is at least. But if it's in that same rock with that concretion that's been compressed, you know the fossil's been compressed. It can help you reconstruct its original shape. Then you know, oh, sorry guys, this isn't a new species. It was just a species that we knew about. It got compressed and it looks different. Or it is a new species and this is what it really looks like. So how are we going to do all that? How are we going to figure out what it used to look like? The tool for that are called Mohr circles. Mohr circles are going to be covered in depth in the next couple of labs, so we'll spend a couple weeks working on Mohr circles. But what they are is a nice, concise way to graphically display strain, so we're not worrying about these tangents and cosines and numbers to try to show somebody or look at it ourselves. We've got something graphical, usually much easier to grasp and convey to somebody, definitely much easier to compare two different things.